through this month's community town hall. This time we're going to be talking about Chroma's evolving architecture and exactly how we're going to move from our current single node product, which is the thing everybody's using today, to our horizontally scalable distributed architecture, which is going to be the basis of Chroma Cloud and lots more besides. And Hammad, I'll let you take it from here.
Cool. Yeah, let's just dive right into it, or do we want to wait a few minutes for people to catch up?
Let's give people a couple of minutes to filter in.
Cool. All right. We will hang out for a few minutes and then we'll get started.
Just as people filter in, we're just giving this a few minutes to let a couple more people catch up before Hammad launches into the architecture discussion. All right, Hammad, I think we can jump into it from here.
Cool, let's do it. All right, hi everyone, I'm Hammad. I wanted to walk you through some of the history of Chroma, why it was built the way it was built. A lot of people still use Chroma v0.3, and we've changed a lot since v0.3. We're now on v0.4, and soon we're going to be shipping a distributed version of Chroma. So my goal today is to walk you through the origins of Chroma as it looks today, and then we can look a little bit forward to the future of distributed Chroma, what that's going to entail, how it's going to look, and how we're evolving the system, as well as guaranteeing that the system works as we expect as we evolve it. Moving from a single node database system to a distributed node database system is not a trivial task, and the whole team here at Chroma is hard at work to do it correctly in a way that will satisfy the various use cases that all of you have. And of course, the main point of this is to inform you, but also to give you a sense of what we're building so that you can contribute, and then also to give you a sense of what we're building so that you can give us feedback. So please, this is not meant to be a one-way conversation. If you have questions, feel free to leave them in the chat and I will respond as we go. So cool, let me talk a little bit about the origin of Chroma. So Chroma actually started as what's called an active learning system to help ML engineers choose data for retraining. And the way we did this is you have some production machine learning model, and every day you get new data. And then we take the machine learning model that you're running in production and we look at the latent space of the model and we extract embeddings from it. Then we actually used Chroma to look at this latent space to determine what subset of data would be worth relabeling. So an example of this is, let's say you have a self-driving car and every day it's out in the wild, it's collecting a bunch of frames of inference, and you want to decide some of these frames are probably useful for me to train on the next time I retrain the model. Chroma basically looked at the latent space of the model to find areas of the latent space that were pretty sparse. So if we saw like, hey, your model actually doesn't have a lot of data in this region, maybe you should label that subset of data to retrain the model. This is kind of interesting, and the way that we did this is using a vector database. And we actually built Chroma because no existing vector database was working for our needs. We had a really real-time use case. We had a lot of fleets of data coming in, a lot of small real-time collections, and no existing provider was giving us what we needed in a friendly, easy-to-use API. So this shape of problem looks really similar to retrieval augmented generation, right? You have some corpus of documents, you turn that into embeddings, you have some input query, and you try and figure out from the perspective of your embedding space, which documents are most relevant to the thing that I'm trying to do, the task I'm trying to perform. We extract that relevant subset of data, and then we condition and generate the language model, hopefully improving the performance and accuracy of its generation. And the historical context of Chroma, because we were building this active learning product, meant that we were doing a lot of whole dataset analytics. So basically, this is on the left a UMAP projection. We basically projected the MNIST dataset running through a convolutional neural net into 2 dimensions. And you can see, right, the training data obviously separates really nicely into 10 classes after we trained the model. And what Chroma initially was designed to do was to choose the data points that lied in uncertain regions, to identify data points that were more incorrect from the perspective of the model in its latent space. And so we built a set of analytics tools to help us do this in an offline fashion. And so we're primarily focused on analytical workloads, right? Large batch processings of embeddings offline. Even though the data stream was offline, the primary computation we did was analytical. And so this led to the former design of Chroma, which many people are still using on v0.3. And if you're using v0.3, please upgrade to v0.4. Please.
I think something like 70% of you are still on 0.3. Please upgrade.
Yeah, you will be a much happier Chroma user if you upgrade. We promise. So there are 3 ways that this old version of Chroma actually ran. Right, we had an in-memory version, a persistent version, and then a client-server version. And the in-memory version basically had a very naive query planner locally that if you filtered your data, it would go to a DuckDB instance, filter your data, and then look them up in an HNSW index to do the actual ANN search. The persistent version did something really similar, but we had a really naive storage format where we basically, at the end of the lifecycle of your process, we would serialize the metadata store and serialize the index. This worked for analytical workloads where like data loss was more tolerable, but it doesn't work for a lot of the transactional type workloads that many customers today are running into. And then the client server model, right, had this additional complexity that you had to run ClickHouse on the side. And this was primarily, again, because we were doing these analytical rollups where we wanted to quickly grab all the vectors in a column or something like that. And it made sense to use ClickHouse. And we had the same sort of naive storage system where basically on process exit, we're persisting the entire thing every time. There's obviously problems with this. And there's a ton of problems. And we heard them from you from February to July when we shipped v0.4. And we tried to address all of them. So the first was dependency issues. People didn't want to build DuckDB. Chroma is designed to be easy to use. You don't want to have to deal with a bunch of dependencies when you're actually getting started. Additionally, you have to run this complicated thing called ClickHouse on the side. It has its own HA story. Also, you have to think about the consistency model between Chroma and ClickHouse, which we just didn't make any strong guarantees around. And then also we had a lot of storage systems that were just optimized for a different use case. We're not really building an analytical product in the same sense anymore. We're building something that's more of a hybrid, and we had like purely analytical tools. And so maybe these weren't the right tools for the jobs that we were trying to do. Also, the developer experience was quite poor in some respects. We put a lot of effort into making developer experience top of mind at Chroma, and some things just weren't quite up to our standard. And we heard this from you, and we fixed a lot of those issues. The first was that we had these really non-uniform deployments. So how you think about resources on your local node versus how you map those resources onto when you deploy. Also, how do you migrate from like this local version to the ClickHouse version? It's not easy to like move between prototyping on your laptop and deploying to actual production systems. And then also a lot of people want to use Chroma for like throwaway jobs where they just want to have some serverless instance, like boots up, reels a bunch of data in, does some workload, and then shuts back down. And because we relied on things like ClickHouse and DuckDB, it was getting really difficult for people to actually deploy to these platforms. The last was we had a ton of performance and correctness issues around the core logic of the data system. So there were just issues with how we did persistence. Like I mentioned, we had this naive serialization scheme. You couldn't use Chroma in a multi-threaded environment without user-controlled locking. So like the intelligent way of saying this would be we were thread compatible, but we weren't thread safe. And we put a ton of work into ensuring thread safety of Chroma from there on out. Also, there were a lot of storage and memory concerns. There was a lot of write amplification in the system, and also, again, this naive persistence scheme. And most importantly, a lot of what we've been hearing from, right, is there's no scale-up or replication path. We get messages in Discord all the time from people who are on Vue 0.3, and they're trying to load, tens of millions of vectors, and then they're not sure how to scale up past that. And our goal is to provide a system with distributed Chroma that helps you think, how do you go past 100 million vectors on a single machine? How do you scale up to multiple machines? Or even if you just want to have read replicas, how would we offer that? So the solution to solve a lot of these problems was the v0.4 release, where we unified DuckDB and ClickHouse with SQLite locally. So we basically co-locate your SQLite index and your SQLite database and your HNSW index on the same machine always. This makes it so there's a single topology across in-memory, persistent, and single node. And you'll see how this maps also to the distributed system, where eventually, and I'll sort of foreshadow here, eventually these individual nodes become indexing worker nodes in the distributed system. And then we also built an actual real storage engine for the index so that we weren't just naively serializing it to disk every time. And fundamentally, the most important thing we were trying to do with this was we wanted to lay the foundations for a distributed architecture. We wanted to get the primitives in the box diagram right so that we could slowly migrate to a distributed system while preserving the API experience of Chroma, so that you can easily and seamlessly switch one day from single node Chroma to distributed Chroma. It'll be the same exact API. It'll be very minimal overhead to switch. That's our goal. So the first version of the storage engine, as I mentioned, was quite naive. We basically had a metadata store and a vector index, and the metadata store was a DuckDB process that at exit sort of dumped itself to disk. That's obviously buggy for a million reasons. The vector index, every write, we would full serialize the index. It's actually surprising how effective this is. To date, I feel I have been quite surprised by how efficient internal page caching on the OS layer was at serializing this to disk, but obviously it's still not really what we want to be doing. So the first thing that we did is we introduced a write-ahead log. So now writes are durable immediately upon acknowledgement to the write-ahead log, and then the metadata store and the vector index have their own storage systems. Since the metadata store is SQLite, that's quite robust in how it actually persists to disk. And now let's talk about how the vector index works. So the vector index basically tails the write-ahead log, and we treat the system as a write-behind cache. So we initially write data to memory, and we keep our HNSW index, which is fundamentally a graph in memory for the most part, which is a set of vectors and the adjacency lists for the graph itself. Periodically, we collect the dirty set of things that we need to flush to disk, and then we actually flush them to disk periodically. We can tolerate data loss because even if we go down while data is still in RAM but hasn't been applied to disk, we just spool back up from the write-ahead log and catch up before we allow the system to resume processing reads. So we made a lot of progress on a lot of the problems that we identified, right? We now have unified storage that's optimized for the use cases that people are building for. We have fixed the build issues with DuckDB and with HNSW. We now ship a precompiled version of HNSW in the core indexing algorithm so that you don't have to worry about that. Also, you don't have to use ClickHouse at all. It's just one uniform single node deployment. And then also, we fixed a lot of the persistence issues, and also we've put a ton of work into making Chroma thread safe so that you can actually just blindly use it for multiple threads and you don't really have to consider anything at all. But there's still a few things that aren't fixed here, and that's what we're working on actively today. The first is it's difficult to reason about resource constraints across the various topologies of Chroma and just in general. A lot of people in Discord are asking like, hey, I have 50 million vector workload. How much RAM do I need? How much disk do I need to provision? And so we have actually a PR out from Treyan in the community who is building a tool to estimate the resource usage of your workload. So you'll be more easily able to guess at least a crude upper bound for how much RAM you need to provision, how much disk you need to provision in order to run an instance of Chroma for your workload or expected workload. And then also we're working on fixing the scale up and replication issue. And that's what the bulk of what I'll talk about today is like, what's our plan around distributed Chroma and how are we building that? So all of this was shipped in 0.4. If you haven't, and I've already said this one, but if you haven't, please migrate. It'll help us, it'll help you. There's many issues that were fixed in v0.4, and if you're still on v0.3, a lot of the issues that you might be seeing will probably just go away. We've put a ton of work into formally verifying or lightweight formally verifying the system to make sure it works as expected. And how have we done this? This has been an important development here at Chroma, is our focus on making sure that the system works the way you expect all the time. And we've done this through a combination of lightweight formal methods inspired by others in industry. So the goal here is to ensure correctness while we maintain velocity of development. We are trying to build an ambitious distributed database pretty quickly, and we want to do this to serve you guys. But how do we do that while making sure everything is correct? So we do this, we have two main testing mechanisms that we've introduced in the last few months. The first is model-based testing, and the second is property-based testing. So the idea is pretty simple. We create a reference model of Chroma. In this case, that's a brute force index, and in-memory data structures to do things like string filters or metadata filtering. And then we basically have a state machine that defines the API of Chroma, and we execute a random rollout of operations. And then we compare that the reference model's results are consistent with our source system. On top of that, for some systems, we may even define key invariants that need to hold at every application of the state machine. So this might be things like we exercise a random add, query, get path over Chroma and over a brute force index, and then we compare the results. But then we also check that, for example, the ANN accuracy is within some certain bound for the Chroma index at every application of the state machine. And this testing mechanism has allowed us to really quickly build the distributed system while ensuring that we're not A, changing the formal specification of the system in the terms of its API design, but also B, making sure that we're not degrading performance of the system. And we're also investing heavily in making sure that we continuously load test and benchmark the system as we build it to make sure that its performance is at least on par with single node, if not better. So one of the goals of this v0.4 release was to, as I mentioned, lay the foundation for a distributed system. So if single node Chroma today looks like this, you have a client, the client writes the write-ahead log, this gets ingested into a metadata store and a vector index, and these have their own persistent schemes, as we discussed, to write to disk. The goal is to very naively, at a high level, break these all out into their own systems. And if you actually go look at the code today, this box diagram is very cleanly modeled in the code itself. And so over time, what we've been doing is breaking each of these out into their own separate services so that we can start to build a horizontally scalable distributed system. And the goals of this system are to A, support real-time indexing. A lot of people have real-time use cases. You have a chat history with a user, you have a document editing system, you have a knowledge base that's updating in real time. These aren't static indices. They're things that update quite frequently, and they have heavy updates and deletes. And also we want to support serverless usage. So we want, if you're not using the data, it is allowed for the system to unload it and then load it back up so that you can minimize your resource usage. And we're focusing on building a cloud-native distributed architecture. And what we really mean by that is we want to build something that exploits the scale and elasticity of the cloud, not something that is built like a traditional database where you have like n nodes and you have to manually scale them up, manually scale them down. We want these things to be automatic and to be mostly thoughtless so that we minimize the pure human labor cost involved in running Chroma. We also want to support pluggable index types. So HNSW is a really great algorithm. It works for a lot of use cases, but it's not always the best choice for your use case. And so we want to be able to plug different ANN algorithms into Chroma so that you can actually run them in parallel or separately. And then we also want to support copy on write branching. This is a feature that I think is quite exciting. So we would be able to support, for example, the ability to send someone a branch of your Chroma database, and it's essentially free from the perspective of resource usage. It's not consuming any additional disk. It's not consuming additional memory. We essentially can just do copy on write branching. And then if you write, then of course we will fork a copy. But this makes it really useful for example, production workflows where some customer says, hey, I have an issue. I give you permission to look at my data. Okay, and then you can just fork their database and then start running tests and experiments on top of it. And also lets you really robustly iterate on your design. Maybe you want to fork a vector database, add some data to it, and see if that improves the performance of your model, but you don't want to re-index all your data. It supports A/B testing like that in a really great way. And then lastly, we do want to support some amount of analytical processing and support being able to run your embedding models for you. And also in the future, in the far, far future, maybe we might even serve your language models in parallel with your retrieval systems, because these two things are becoming more and more interlocked with another. And so these are the key goals of the system that we've been trying to design. And again, all of this is in service of building a real-time system for AI memory. We want to make it so that it's thoughtless for you to fire documents into a system, have it ingest them, have it update the embeddings, and then also give you tools to enhance the quality of your data over time so that you can make the performance of your application both quantitatively and qualitatively better. And one of the key insights for the system design is the idea that the log is the database. And a lot of the system design tails off of this idea. So the key notion is that when you write data to a log, that is a record of what you've done and therefore is the database. And everything that happens after that fact is mostly a function of your consistency guarantees, i.e. how do you want to be able to read your own write, how much data lag can you tolerate, and then also a function of how you materialize the actual database, which in our case is as an index. And so what I'll articulate is the write path of the system and the read path of the system. So before I do that, let me just quickly explain these boxes, right? What are these things? So the Chroma server is essentially just the front end of the distributed system. It takes in API requests and it forwards them to the log. This will look really similar to the diagram we just looked at 3 slides ago from the single node diagram, single node system where you have a client that writes the write ahead log. The only thing is now we have to have a server in between. The Chroma server is a horizontally scalable front end service that basically just knows how to write your entries to the distributed log for a given collection. We have a fleet of indexing nodes that can then tail the distributed log, write it internally to their indexes, and periodically they flush to object storage. Object storage becomes the source of truth, and then if indexing nodes crash at any time, we can spool back up the state of an index from a combination of the log and a last known checkpoint in object storage. So and in this way, indexing nodes are actually horizontally scalable and completely stateless. We're not like mapping an indexing node to a collection or anything like that. They're allowed to fail and they come back up. And all of this assignment between collections to indexing nodes and Chroma servers to the log is handled by a control plane, which consists of a coordinator and the system DB. And the coordinator basically just keeps track of cluster level state. It knows which collections live on which indexing nodes, it knows which Chroma servers are assigned to which parts of the distributed log, and it knows where the different checkpoints for collections live in object storage. So when you write to Chroma, we essentially do the same thing we did before on single node, just everything is a separate service. We write to the Chroma server writes to what is functionally a write-ahead log, or an event sourcing pattern, if that term is more familiar to you. And then those get ingested by indexing nodes, which flush to object storage. And then the metadata about how the system is actually kept in state is held by the coordinator. The read path then looks slightly different. On the read path, we don't have to go to the log. The Chroma server just needs a mechanism to figure out where the data it needs lives. And then it goes to the appropriate indexing nodes. Those indexing nodes locally run their queries on the various index types, and then the Chroma server can aggregate those and return them to the client. A key to this is the internal data model. So our external facing data model, as many of you are aware, right, is just we have these collections. You can query a collection, you can add to a collection, do other CRUD operations on a collection. But internally, one of the key goals of the distributed system is to be able to scale a collection up past a single node. So we do this by introducing the concept of a segment. And a segment you can think of as like a generalized notion of what other databases might call a partition or a shard, but it's a way to compose a hierarchy of different pieces of data in order to satisfy a query. And you can see here on the left, we have like an idea of like one particular way that a segment might be optimized, right? Or a collection might be spread out amongst segments. So you have like an HNSW segment that might actually be sharded into 3 segments. These segments might live across multiple machines. We may also give you like a brute force segment. And this brute force segment would allow for doing things like if your data scale is small, there's no reason to build a online HNSW index if your data scale is small. We can just store it in a brute force segment. And then in the future, as I mentioned, we do want to support plugging different indexes in. This might be things like disk ANN, or things like maybe just classic KD tree type approaches to doing approximate nearest neighbor search. Whatever the actual index type is, we want to be able to support it. And so our data model has been designed from the start to support A, multiple index types with their own respective partitioning schemes, but also B, the ability to have more than one index and support zero downtime switches between them. So you could imagine at first a collection just has a brute force segment. As it fills up, we switch to an HNSW segment once your data scale is large enough to warrant and justify an HNSW segment. So key to this is how do we actually shard the data, right? I've just sort of hand waved here and I've said an HNSW segment is composed of multiple. Well, how do we actually figure out, what this partitioning scheme is and how do these segments get assigned to different nodes? So let's talk about that. So the goal here for segment-based sharding for the HNSW segment is to do a time-based sharding approach where basically we break the HNSW segment into many, many segments. And initially, a collection is just composed of one segment, and we call that active. And as indexing nodes read from the distributed log, they write to the segment that is active for a given collection until it reaches a maximum configured size. At that point, we seal this segment. So we tell the coordinator, hey, this segment's full. Based on some maximum size, and we register a new one. And then the coordinator allocates us a new segment. So this indexing node then has now just not one segment, but 2. And we call this sealed segment a historical segment, and then we call the new segment the active segment. And the goal here is that as a collection grows, we basically just get this append-only data structure of indices. And in the background, we can compact these, we can move them to more efficient index types, or we can do things like move them onto separate machines altogether. There's no need that a given segment, once it's historical, lives on the same machine that it was created on. So this allows us to scale segments up past a single machine. As the collection grows, so do the number of segments, and then historical segments may get rebalanced across other indexing nodes. And key to this is how do we actually tell different indexing nodes which segments they're responsible for? And so there's 2 tiers of assignment. The first is these active segments, and the second is the historical segments. And we treat assignment of these 2 as separate problems. For active segments, the way we assign them is we actually assign based on the topic from the distributed log. So the distributed log, if in the case of something like Pulsar or Kafka, exposes the abstraction of a topic. And what we do is we do rendezvous hashing, where we basically take the segment ID and then the machine ID, and then we apply a hashing scheme in order to decide which indexing node is responsible for that active segment. And this gives us a way to make sure that topic assignment is stable over the lifetime of a collection. So if no index nodes crash, And a single machine is always responsible for the active segments of a given collection. And then we treat the historical segments as a different pool. And we basically hash over the historical segments and assign them to indexing nodes. So important here is that once a segment transitions from active to segment in the flush and register procedure that we just saw, it may move from one indexing node to another. And another detail here is that every indexing node will manage its assigned segments locally in LRU fashion. So we basically, a given indexing node may be assigned many, many, many segments, and it may not need to actually serve all those segments. Maybe some of those segments, are distributed like Pareto. So like 20% of the segments actually consume like 80% of the writes. That means we can keep most of the segments off memory for most of the time and just keep them on disk and load them up on demand. And the idea is to think of the system as locally eventually converging on the optimal distribution of segments. Obviously, that's not the case, and we have plans for how to make this better over time. But this is the first version of Chroma will support locally doing LRU over the segments and assigning a vast amount of segments to each individual machine. So just to zoom out for a second, like what did we just talk about and what did we just cover? So we just covered how the distributed log knows how the indexing nodes know which segments they're responsible for. And the way indexing nodes know which segments they're responsible for is through this hashing scheme, where we hash the topic and assign it to an indexing node, and then we hash the historical segments and assign them to different indexing nodes. So I have a question here from Vaughn. So what I mean by topic assignment is stable over the collection life means that at steady state, let's assume no nodes are being added or removed. A single indexing node is always responsible for the active segments for a given collection because it's assigned that topic. A single topic might have many collections, and I'll explain how that works in a second. So a single topic will have many, many collections that are actually being written to it. So there's many logical log streams on each topic. So when we assign a topic to an indexing node, it's actually implicitly serving many, many collections. In that case, we basically don't want for the active segment to be changing between nodes very frequently because creating and destroying those subscriptions to the topic involves some state transfer. So we want to minimize that. So the goal is this topic should only ever be assigned to one indexing node, and we want to switch it over not very frequently. So the goal then is we treat the active segment assignment as a different problem than the historical segment assignment. So if indexing nodes never crash, then the topic will always be assigned pretty stably to one indexing node. The only time where it gets reassigned is if indexing nodes get added or removed. Hopefully that makes sense. So now let's talk a little bit about how front-end servers get assigned different collections and how we actually do the thing I just discussed where different collections actually get multiplexed onto a single topic. So the way this works is you have many, many collections, right? We have all the collections that exist in a Chroma database with potentially many, many tenants. And what we do is we do a hashing scheme, again, the same hashing scheme we were doing in other places, and we assign them to various Chroma servers. This ensures that a single collection only ever has a single writer for a given collection to the log. This is how we preserve ordering guarantees on the log. We don't want your writes to get reordered from under you. This would obviously be bad. Then there's another element to this is how do we take multiple collections and multiplex them onto a single topic in the distributed log? And the way this works is much the same. We take all the collection IDs, we do a hashing scheme on them, and we assign them to different topics. There is, of course, work here in how do we, when we need to rebalance the number of topics, how do we fail this over in an elegant way? And I'll talk about some of the mechanisms we're doing that, using to do those things like that in a second. And then basically how you can think of this is each topic is many, many, many multiple log streams per collection that are on one physical topic on the actual distributed log system. And then consuming indexing workers can filter this into the logical log streams that they care about for the collection that they're writing to, or more specifically for the active segment that they're writing to. And these mechanisms lead to an information propagation problem, which is in order to satisfy a query, a front-end server needs to know two pieces of state. They need to A, have knowledge of the segments belonging to a collection, right? They need to know, I have a query for this collection, what are the different segments for it? And then they also need to know where these segments are, which machines, which workers actually have these segments currently so that I can issue a query to them. Because a collection might be sharded into many segments, those segments might live on multiple machines, and the Chroma front-end servers need to go and query all of them, and then locally reduce and merge that list in order to satisfy the end query. So basically, they need to have this shared state, and the shared state is the worker member list, the front-end server member list, and the collection to segment mapping. All proxies need to know what the different workers are, all front-end servers need to know what the different workers are, and all collections to segments, all of the front-end servers need to know the collection to segment mapping, so they know where the different segments are, what the different segments are for a given collection. And so I will take the example of the collection to segment mapping and show how we propagate that state throughout the cluster. So just to make it very clear, a Chroma server needs to know all the different collections for a segment. Hopefully this makes sense because it needs to query all of those segments, and those segments might live on different machines. But new segments are being created continuously, and they're being created by the indexing workers by talking to the coordinator. And this leads to a problem because an indexing worker could register a new segment, and then the Chroma server would have no idea that it was created, and it would have an impartial query. It would only query the segments it knew about. And we want to prevent stale read situations like this. Again, Chroma is eventually consistent, right? Because we use this asynchronous distributed log write pattern, but we still want to make sure that eventually you will get the right result. So how do we do that? Basically, when an indexing worker registers a new segment, it will update the version number, or we call this the epoch for a collection to segment mapping, and it will add a new, the coordinator will add a new segment and then tell the indexing worker that it's updated the version. The Chroma servers still see the old version of the data. They see that I have one segment for this collection and it's at V0. Let's say then that this Chroma server goes to query. At that point, what will happen is the Chroma server will talk to the indexing worker, and the indexing worker will see that it actually has V1 and will reject the query because of a version mismatch. Then what happens is the Chroma server refetches this information and updates its state so that it's now at V1 and it has two segments. It then refetches the data from the appropriate indexing workers, and for sake of argument, let's say that in this case, one of the historical segments actually moved to a different machine. So this is the mechanism that we use for pretty much all global state that the cluster needs to maintain. The worker member list, the proxy member list, the front-end server member list, as well as the collection to segment mapping. All of these are maintained by this pretty simple system where we have version numbers in the consistent core of the coordinator. So the coordinator always has the main source of truth of the system. And then at least one node in the participation group always knows the correct version at all times. And then we can do this local reconciliation when a Chroma server talks to an indexing worker or other systems coordinate with one another where they detect a version mismatch, locally reconcile with the coordinator, get the correct state of the world, and then retry. Obviously, this is not good in the case of steady state. We don't want to always be querying the coordinator in the right path. So we also have a mechanism to asynchronously propagate this information. So the majority of the time, the Chroma servers will have an up-to-date view of the world, and then occasionally they will run this version mismatch in the case where the asynchronous propagation had too high of a delay. So in those cases, we still guarantee correctness through this local reconciliation. But from the perspective of the protocol that we've designed, this asynchronous path is purely an optimization, and you could just only rely on the local reconciliation at all times. So the update conditions for these different pieces of state are pretty clear and obvious, but just to clarify, we update the worker member list whenever a node gets added or removed, and front-end servers use the worker member list in order to determine where different segments live. The front-end server member list is used in order to determine the sharding scheme for collections onto topics, and that gets updated whenever a node gets added or removed. And then we have the collection to segment mapping, and that gets updated whenever a new segment is added. And whenever these updates are triggered, we increment the version list and then sort of asynchronously propagate the state throughout the cluster. And whenever there's sort of a coordination point where one node talks to another, they will locally reconcile, and we maintain the invariant that at least one of those nodes will have an up-to-date state of the world because they talked to the coordinator in order to issue that version change. And all of this is targeted for v0.6, which we're targeting for an alpha at the end of November. So if you're curious, hopefully by the end of November, we will be releasing a private technical preview or an alpha in the open source product of this system so that you can try it for yourself, or you can try it on our hosted product. So this same distributed architecture that I just talked about is also what we are using for the hosted version of Chroma. Many people have told us that they don't want to run their own infrastructure, so we're going to run it for you. So the goal is to launch the open source product in very, very early alpha in November alongside a private technical preview. So if you're not on our waitlist for the hosted product already, please go to our website and sign up. And the near-term product roadmap. So we don't want to only focus on the distributed system. There are also a lot of important product features and developments that we want to build because we've heard about them from you. And also we think these will be useful things for you. So the first is we want to support multimodal embeddings. Right now, a lot of people have been using newer multimodal models that support embedding images or text. And we want to support that as a first-class citizen inside of Chroma. We also want
More
to
importantly, multimodal embeddings have been around for a little while, but very shortly we're going to have API access to the multimodal understanding models themselves. Things like GPTV will be available over API. Things like Gemini will be available over an API. And we have multimodal open source models, which are performing reasonably well too. So this needs to be a first-class citizen in Chroma. I'm personally working on this right now.
Yeah, Anto, do you want to talk about feedback and embedding model registry since you're working on those too?
Yeah, might as well. We think feedback is a really important component in basically in how a retrieval system ought to work with AI. So what I mean by feedback specifically is the ability to collect evaluation signal about the quality of retrieval augmented generation and of the retriever itself, so that we can automatically adapt the embedding space, whether by fine-tuning the embedding model or applying affine transforms directly in that embedding space, to basically automatically make your retrieval system better if you have your eval set up. And we're building that out as an API input in Chroma so that you can plug it easily into any eval system you want, whether that's something off the shelf or whether it's something that you've built in-house custom for that. And finally, we're building the embedding model registry. This is something that has long been a desired feature in Chroma. Anyone who's loaded a Chroma collection without supplying the right embedding function has run into the issue that we're working to fix here. But essentially, it's about being able to preserve which embedding function goes with which collection in a way that is automatic and seamless for you, so you don't have to work with that yourself at all anymore. That's the overview.
Cool. Yeah, and these things are all we're actively working on them, and we'll follow the same open source process we always do. So you'll see a chip, a Chroma improvement proposal go up on GitHub. When you do, please give us feedback on what we're building and how we're building it. And there's one thing I left off here. There's a surprise, I guess, which is we also want to support multimodal, not multimodal indices, sorry, user-defined indices. So this would be the ability to specify your own index. A lot of people have been running into performance problems where they have some metadata filtering pattern and they want to be able to support defining their own index over those things. And so we're actually actively working on that as well. And you can see an open PR for it. Cool. And as always, our commitment to you. We want to focus on developer experience and productivity. These are first-class parts of the experience of using Chroma, and we will never sacrifice them in order to make something better or to make something more performant. Our general philosophy is to think of things like a progression ladder rather than to think of things as incremental steps. So how can we make it so that Chroma has the power, but incrementally reveals it to you? The second is to develop incrementally and in the open. So we're doing a lot of things. We're doing them pretty fast, but we do want to involve you, both from a feedback perspective, but also from a building perspective. We get a ton of great contributions from the community. Every week we review PRs from people all over the world, and it's A, exciting and invigorating, but also B, just really useful to us to hear how you want to shape this product and build it together with us. And the last is when we ship major breaking changes, we will give you the tools to migrate. We shipped a very useful CLI tool to migrate from v0.3 to 0.4. And we will do so if there's ever a need again. We treat migrations very seriously, and if we do need to migrate in order to move to a new system or a new data model, we will always give you tools to do so. It will not be on you to manually change your code or your data. Cool. With that, that's the end of my talk. If there's questions, we're happy to take them. And then also, please join GitHub if you want to learn more. If you're not on our Discord, join our Discord, and also feel free to ask me things directly. I'm on Twitter and open to hearing feedback or questions about Chroma.
Great. Yeah, thanks very much, Hammad. And I'll open it up here to Q&A. There's the Q&A tool over on the right. I see one question already, which is, can you demonstrate an AWS serverless use case with the index saved on S3 and operations performed by Lambda? I mean, that's very concrete, but Hammad, perhaps you've got something to say here.
Yeah, let me find this question. If I understood correctly, someone wants to use, let me just read this. Yes, we totally can make an example for that. We will work on this. I think this already, people are doing this today. They run Chroma in a Lambda, and then at the end of the life cycle of a Lambda, they'll dump to S3. Depending on your use case, that is valid. So we can definitely have an example for a use case, as well as when it, how you would actually do it.
Thanks so much. Any other questions from the audience? Feel free to use the Q&A tool. All right, cool. Well, I guess if there aren't any further questions, we can wrap it here. Thanks very much for presenting in such detail, Hammad, and hopefully that gives the Chroma community a great understanding of the history, a little bit more about where we're going, and as our sort of architecture solidifies, some insights into how and why we're making the choices that we're making. And as everybody here knows, we're building this specifically for AI. Chroma is not a general purpose vector search and storage solution. It is retrieval specifically for AI applications, and that requires making very specific trade-offs and great architectural decisions along the way. And I'm really glad to be a part of this team that's achieving these things. We are hiring. If you'd like to join the Chroma team and work on some of this stuff, please check out our careers page. It's at trychroma.com under careers. And hope to hear from you soon. And until next time, until the next Chroma Town Hall, thank you very much.